I start with students that whenever you see two things that are in parentheses like this, okay, I have a set of parentheses here and a set of parentheses here. That means multiply. And sometimes students aren't always used to that.
And do the ones like in the
Okay.
first set, like like the PEMDAS rules, like to do your parentheses and exponents
Okay,
first.
so for those of you who are going ahead and doing this, go ahead and do this. For others, I want to kind of talk you through what I would do.
Okay.
Okay, so on your calculator, I would write, this is what I'm going to write, CALC. So on your calculator, you're going to put 4.55 on your calculator. Then you are going to find the scientific notation key, that fancy key. So after you put 4.55 on yours, I think, then your fancy key is EXP. So some people, I'm going to put a series of keys. You're going to either hit, not only one of these, you'll either hit EXP, or you'll hit EE, or you'll hit SCI. One of those. Oh, I'm sorry. I'm glad you helped yourself. Did everybody get a calculator? Okay. So step 1, okay, is to put in the coefficient, 4.55. Step 2 is to hit one of those. Step 3 is going to be to put in what the power of 10 is. And the power of 10 is, you're going to enter 13. Yep. All of those steps right there, these steps 1 through 3, are just getting ready to put in this number right here. That's all those steps 1 through 3 are.
So when I hit equal.
Yeah, don't hit equals. Simon didn't say hit equals.
Oh. Good, because it didn't do it.
Okay, so once you get the first number in, then it's a regular multiplication problem. And then what I would do is hit the multiply key. Well, I'll shut that, but. Okay, and then enter the number 7, and then hit equals. What you don't ever do, and I'm not going to even put it up here, what you do not do, and I understand the concept, is you do not do 10 raised to the x power. Do not. Pretend like it's not even there. You may have used it in the past. It may ultimately get you down the road, but it won't get you down the road for this course, which is, another 15 weeks or so. Do not hit 10 to the x power. So somebody tell me, somebody who's brave, we're going to do this like when you balance your checkbook, which I never do anymore. You look to get the same number twice. So let's see what sort of numbers we got out there. Somebody tell me the number they got.
3.185.
3.185 times 10 raised to what power? 14th. Anybody get anything different? How many people got that? Yes. You can borrow a calculator, Harley? Okay. All right, so this is all looking pretty good, people. Let me know if it doesn't work. Okay, so let's do the next one.
And that's the format you would like us to leave it in?
That we're going to be talking more about rounding today, which makes people, and I'm going to show you have to actually truncate. You have to truncate the coefficient, usually. Okay, we'll talk more about that, but for now, this is what I wanted you to do on your paper. So get that on your paper. So go ahead and do the next one. I'll kind of doodle underneath it what you'll need to do, but you already know. The first number, since it's in scientific notation, you enter the coefficient, 6.09. Okay, and then you hit your EXP or your EE or your SCI, one of those, okay? And then you enter, now this one, since I'm just kind of talking to myself, you guys have already been doing this, but since it's raised to the 26th power but negative 26, this time you have to find the negative key that's different than the minus key, okay? And then enter 13, okay? Now, I'm pretty sure if you were to go ahead and enter right now, it would just go ahead and pack it up and it would display it to you. But let's go ahead and finish the multiplication. Of course, since I have parentheses here and parentheses here, what I'm going to do between them is multiply. So then go ahead and hit your multiply button times 3. Okay. So somebody tell me what you got for the coefficient.
1.827 times 10 to the negative 25th power.
I got the negative.
Okay, that's okay. Well, I mean, it's not okay, but... So how many people got to the negative 25th? How many people got to the negative 24th? Dang it. Okay. So it's like if I was bouncing my checkbook, I'd go with the negative. Which I hope I have more money than that, right?
That is owing a lot of money.
That is. Well, no, it just means a fraction of a penny. It's not a negative amount. So go ahead, if your name's on those, rip those out and hand them in. It's also a good way to take attendance, but the extra 5 points doesn't hurt.
Well, I'll take them anywhere I can get them.
Yeah. If this was seemed a little kind of odd or queasy to you, you'll have more practice at this. Okay. Thank you, ma'am. Thanks. So yeah, like someone was asking, is that the number that you need to write down? Is that the right number? Well, we need to talk about rounding. The other thing that drives me nuts about these numbers is they are what I call naked. Ooh, your hands are cold. There are no units at the end, like it's not inches or kilograms or meters. And in general, there are very few naked numbers in physical science. There's usually, you got to say what it's just.
I noticed that in the
units.
homework
Yeah.
assignment that we turned in.
Yeah. Your book is really pretty good about
So I think two of the problems
wanting to.
were naked as you call them, and the two had a unit.
Okay. Oh, all right. Okay, so let's look at how we're leading up to rounding, and we'll talk more about rounding on Wednesday. But before we talk about rounding, we need to actually talk about measured quantities that talk about inches or meters or centimeters, okay? And we need to talk about what we call significant figures in that number, okay? Significant figures, okay? So first off, whenever I say significant figures, it's the same thing as significant digits, figures and digits, okay? But basically, when I said thou shalt not lie, when we're kind of teasing about rounding numbers, okay, we're leading up to this on Wednesday, but ultimately this is going to, counting significant figures is one of the players in how do you round a number, okay? So when somebody does it correctly, and they give you a measured quantity, like so many feet, or so many seconds, or so many moles, when somebody does it correctly, they give you that number, and they are actually telling you the uncertainty in that measured value. So it's not done haphazardly, which we should appreciate, because actually there's a reason why they are so careful about how they report a measured quantity. So significant figures, we'll be counting them today. And I brought me a little printout to remind me of the page. Here it is. Rules for significant figures. This is one of your slides coming up. Okay. So all measured quantities have uncertainty in them, okay? But I'm going to tell you one broad type of number that there is no uncertainty, okay? It's exact. But aside from that, we have these issues of being accurate, and we have these issues of when we measure something, how precise are we? When you get something, when you send a sample away for analysis, whether it's an environmental sample or a forensic sample or whatever, okay, they're going to run some tests, and they're going to tell you how accurate it was, based upon the instrument they used. And they're also going to tell you what the precision was. Sometimes the precision I kind of put, and you'll see why this is scatter. Precision is scatter. Okay. And accuracy is accuracy. Accuracy is, I'll just emphasize how close it is to the true or accepted value. Sometimes it's hard to know how accurate it is, but instruments are run with standards to know how well they're performing. So, okay, so precision is scatter. So this actually, if you're throwing darts, you want to get a bullseye, right? Okay. And one of the things about doing any sport is being able to reproduce your ability, okay? So how reproducible are you and how good are you, okay? So here, you know, the person doesn't hit the same location and they're definitely not even kind of scattered around the bullseye. So we say the accuracy is bad if the bullseye's his or her goal, okay? And the precision's not very tight, okay? So here we say that they still need glasses. He's reproducible, so the scatter's low, so the precision is good, okay? But if his goal again, or her goal is try to get in the center, not accuracy's off. So obviously there's another scenario, and that's this, where nice and tight, good precision, and getting it where it's supposed to go. I guess I would argue that there's one more possibility. I'm going to draw another bullseye here. Okay, this is where it's supposed to go. Okay. So how about this? What if they get one right in the bullseye, and then they get kind of equidistance from the bullseye? What would you say about the precision? Not very good. If you averaged all of those, what would you say about the accuracy? Not bad. You know, it's kind of taking a spatial average can be done, okay, but kind of on an average, not bad. Okay. So that is accuracy and precision.
So the average accuracy would be okay on that one?
I think if you would average those 5 darts, they kind of, to me, average in the center. So to me, accuracy is not bad. Precision, has left something to be desired. Okay, that's just kind of somewhat of an aside, but I think you get the idea between accuracy and precision, thinking about darts. Okay, so if it's how off a number is from the real value, again, sometimes it's hard to get the real value. Sometimes we just use the average as the real value, but we call that the error. Okay, error is associated with accuracy. Uncertainty or wiggle is associated with, I can't repeat it. But honestly, sometimes it's not the investigator or the lab person's fault. It's just inherent in the equipment or how low they're trying to detect the quantities. Okay, so uncertainty is associated with precision. Okay, so error, how far off you are from the real value. Okay, uncertainty is basically looking at the interval between your measurements. Beware of the lab that only runs a sample once and goes with that analysis. You're like, dude, repeat it. and do the analysis. You know, it's like a statistics thing. You know, come up with kind of what sort of spreads you have. So then there's absolute error and relative error. Okay, so absolute error is a subtraction. Absolute error, you just do a quick subtraction. How far you is probably your average value from the true value. And then relative error is a division. Sometimes in here I do talk you through doing a relative error in the lab. But the division for relative error, basically you put the error, absolute error, I'll put ABS for absolute error, divided by, that means ratio, absolute error divided by the true value. I always think of the hardware. Okay, and to get it into parts per 100, oftentimes we multiply by 100%. Okay. What this takes into account is, so you know you're off, right? You got the absolute error, but if you divide it by kind of how large the real value is, then you can kind of get a sense for this really big deal. So maybe your error from comparing your accuracy to the real value is like 0.1, but maybe your true value is 1005. you're like, dude, that's awesome. Okay, if you come up with an error of 0.1, an absolute error of 0.1, and your real value is like 0.6, it's not real good. So, if you're in the business of analyzing stuff coming from a lab, these are really important. And you'll be creating data in the lab, so okay. So no matter how good you are, you're never gonna get, well, I should say, there's uncertainty in all measured quantities. I'm gonna show you 2 exceptions coming up. If it's by definition or counted, there's no uncertainty. But otherwise, there's uncertainty in pounds, there's uncertainty in grams, there's uncertainty in inches, there's uncertainty in kilometers, okay? And significant figures is one way that you tell where the uncertainty is. So it's an important thing. Okay, so significant figures is one way to tell. So on Wednesday, after we talk about significant figures, here today, on Wednesday we're actually going to do some multiplication and addition and subtraction. And how do you round your answer? But does this make sense? That if you wanted to, let's see, what's a good example? If you had just like a square, okay, and you wanted to get the area of that square, of course you would measure the length and the width, however you want to say that. And then to get the area, you'd multiply those 2 together. But there's uncertainty in the length, and there's uncertainty in the width. And you multiply them together, and there's uncertainty in the area. Okay, that's what I'm talking about. Okay, we need to know how to say what the true area is. Okay, so significant figures. We could have this number, and if I said this was like 4.1267 inches, 4.1267 inches. If I put inches on it that you think of, I know, you're like, really? Somebody can measure that? Well, I don't know, it could happen. The more the nitty gritty of the measurement you want, the higher or more costly the equipment. Okay, I agree. But if somebody really did do that, and they said they understand that they're showing the right number of significant figures, then basically what they're saying, and you're going to see this kind of blue-red convention, what they're saying is that they know for certain that length is 4.126 inches, and there's wiggle room in that last digit. We say there's wiggle room, or that last digit, which is, let's see, 10th, 100th, 1,000th, 10,000th of an inch. They're like, I'm not quite sure about that digit. Okay. So sometimes in my convention, I'll go like this. I'll go, yes, 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 question mark. Okay. Sometimes, and you're going to see it here in a minute, sometimes we'll say that's plus or minus 0.0001, usually, inch. Does that make sense? I know this, but I don't know that. So, honestly, and it's always going to be that last digit. So, if somebody says, I've got a chunk of hamburger here, and it's 1.75 pounds, 1.75 pounds, my chunk of hamburger, we know it's 1 pound. We know it's 0.7 pounds. Okay. But that last digit, again, it's like, I don't know. Okay? That would be where I put my question mark. That would be the red one. So honestly, that's the way people do it, if they're doing it correctly. So it's kind of a forced, the hand is forced by the measuring device in a sense. So one of the things you're going to be doing in your lab, in the lab Thursday, is would you call those gradations, I'm hoping? Do those look kind of like gradations to you?
Yes.
Okay, good. There are different sort of gradations. They're not on a beaker or anything, okay?
Closer, set closer together.
Yeah.
Resolute.
What's that?
It's the Heisenberg recipe right there on top of the scale.
Hey, don't even talk about that blue stuff, right? But one of the things about gradations is I'm going to have you estimating between the gradations. Now, we don't have a balance like this. We've got fancier balances, okay? Right. But up there at the top, you can see that they've already written what the mass is. Okay, 1.2 grams. And can you see where they got that? Okay, basically, they looked at each of these, I don't know, I kind of marked it. Bless you.
Bless you.
Thank you.
Let me kind of erase this. So, bless you. Each one of this is 5 grams, okay? And so each mark is 1 gram. So can you see where they clearly went is 1 gram, and then beyond 1 gram, this person, this experimenter, kind of estimated between the gradations. Okay, so 1.2. So where would I put my question mark on that 1.2?
2.
Over the 2, exactly. Okay, it's uncertain, and I would put a check mark there. I know it's clearly at least 1 gram. So kind of a similar thing. Oops, come back. The next one shows something else. It shows mass again, but a different type of scale. Okay. The dial, this is kind of an old-timey thing. Again, we have digital, don't we? Yay! Okay, but what you used to have to do was, isn't that adorable? It's like a pistachio. Who thinks of these things? Okay, and there would be like blobby things over here where you could, if you've used this kind of pounds before. But here, there's no blobby things, it's just on the other side of a gram, 1.26 grams. And do you see where the investigator, actually, in this case, it's not 1 gram, it is, yeah. So if this is 1 gram and this is 1 gram, each mark now is a tenth. Okay, so he went 1, he or she, and then 0.1, 0.2, so 1.2 for sure. And then again, estimating between the gradations. I know sometimes you're like, really? I gotta do that? But yeah. I'd almost say kind of halfway between the gradations, but they went, like a sixth of the way. Or 6/10 of the way, so. Does that make sense? Okay. Okay, so anytime somebody tells you, oh, by the way, 1.26 grams, so where is the uncertainty? Over the 6, exactly. So I put a check mark the 1, the check mark the 2, and a question mark over the 6. Okay, so there are some numbers that there's no wiggle room in them, and they fall into 2 broad categories, and you're going to hear me refer to them throughout the course, okay? So one is by counting, okay, and the next slide, it has coins there. You're like, dude, there's no uncertainty here. I can count the coins, okay? The number of people in this room, we can count the number of people. No, don't insult our intelligence. So exact number by counting. The other one is by definition, okay? And the example I have coming up is actually when they set up the English system for length, okay, they set up, feet, they set up inches, feet, yards, etc. And how many inches are there in a foot?
12.
Right. And that is by definition. They set it up that way. No wiggle room there. Okay, so that's the 2 ways where you don't have to, it's exact. And we'll talk about how that has consequences. So there are exactly 7 coins there. No plus or minus 1, right? Okay, and again, I told you it was set up by definition within the English system. Here's another exact relationship. Oh, a couple things I want to say. So you guys told me that 1 foot, you told me, is equal to 12 inches. And actually, I'm going to put the word exactly. I'll put a smiley face. I want to switch from English to the metric system, if that's okay with you. Let's see, how's this? Fill in this blank. 1 kilometer is equal to blank meters. What number goes there? 1,000. And that's one of the things you're supposed to be kind of working on. Is anytime you see kilo, it's 1,000 times the base unit. In this case, the base unit is a meter. So 1 kilometer is equal to 1,000 meters. A few things. Those are equivalency statements. statements, and we'll be talking more about those on Friday. Equivalency statements. Oh, wonderful. Is there any uncertainty, or can you see where that purple one, the metric system, that's exact? Does that make sense? It's by definition it's how they set up the system. One more. All right, something you're supposed to memorize. You don't have to memorize much between the English and metric system, but I told you you need to commit to memory. 1 inch is equal to how many centimeters? Thank you, 2.54. Perfect. And when you saw that equality, remember what was after it? Exactly, or exact, same thing. That is by definition. And I don't know historically how they did that, but I'm glad they did. You know, it's an exact relationship between the two, the English and the metric system for length. Okay. All right, so this is where I printed one of these out. And if you want to, there's 5 here, you want to kind of go point them 1 through 5, you can. So let's just say someone gives you, somebody gives you a number, and they're like, hey, it's inches or grams or centimeters or kilometers. And they're like, dude, before you kind of consider this number fully, you need to count number significant figures in that number. Okay? So here's your checklist. And basically, you go, and I usually just kind of check the digits or the figures that fall under these categories. First off, if it's not a 0, it's significant. Okay? Second off, okay, if it is a 0, and zeros are the things that get us. If it is a 0, but it's stuck between 2 non-zero digits, it also counts. Okay?
How does that work?
I'll show you. I can definitely come up with an example. So this one, like if we had 1,023, okay, that's an example of the, if I was going to go ahead and apply the first rule, I would do check, check, check. And I know I've been putting kind of a question mark over the 3 to show uncertainty. But it's a significant digit. Okay, and so according to this rule,
The 0 is significant.
the 0 is significant. Exactly. So that's rule number 2. I wish these didn't go away, but they go away when I click this. Okay, trailing zeros after the decimal place. Okay, now this is not what we call an implied decimal place. This is a hardcore, somebody took the ink to put the decimal place. So let me show you an example of that. Okay, so if somebody has 12.500, where's the decimal? Between the 2 and the 5, that's the decimal. These zeros over here, we call trailing zeros after the decimal. They're trailing because there's no other non-zero digits after them, so they are trailing. So I'm going to go ahead and put, according to rule number 1, 3 check marks. And then according to this third rule, 2 more check marks. Those are check marks. One of the things is, and I kind of tease, but it's true, if this actually were pounds, and somebody says I have that many pounds versus 12.5 pounds, okay, can you see which measuring device, A or B, costs the most? A, yeah, you know.
It's also more exact because the 12.5 on the B could actually be like 12.523.
Right. This brings accuracy and potentially accuracy and precision, exactly, more.
So the trailing zeros are significant because they show that it is accurate.
The trailing zeros are significant because they are showing that actually, if you want to go with this plus or minus, this plus or minus 0.001 is what we call the wiggle room in that particular measuring device. Yeah. Here, what's this one? Mm-hmm. Yeah. They're two different measuring devices. So how many significant figures in this one?
1, 2,
3.
3.
oh, 3.
Mm-hmm. 3. And you're going to see me use this the symbol, or not really a symbol, but the abbreviation SF. 3SF. 3 significant figures.
The only reason I said 2 is because I figured the .5 would have been the uncertain question mark because of the last digit after the decimal.
Right. Uncertain digits they're always you can only keep one, and you're right, that's red hot uncertain, but it is significant.
Okay.
Yes.
Do
Okay.
we see that SF abbreviation a lot?
You
I
will.
mean, I did write it down, but.
Good. The SF abbreviation, I don't even think it's in my notes, but I use the significant figures, SF, when I'm grading your stuff, your homework, and I say, oh, check your significant figures, and I'll just,
The circle or check.
yeah. So
something,
SF
marker.
means
Okay.
you didn't write, you need to check your significant figures.
Okay.
Yeah. Okay, so the fourth one, again about zeros. Okay, and this actually has to do with, if you want to put just small numbers, you can. This only is limited to small numbers if I think about it. And I'll show you why. Small numbers only. Leading zeros are never significant. And these actually are going to, I don't know how to describe this. I think I'll leave it just like that. But here's an example of leading zeros. 0.000057. So I have 4 zeros and then a 5-7. Oh, another thing. Sometimes students don't really get in the habit of putting this 0, okay? And you don't really have to put this first 0, but I like to do it because then it kind of emphasizes my decimal.
So what if that was 1.00057? They'd all be significant, wouldn't they?
Right. So, but let's finish this thought. So, according to Rule 1, of course, 5 and 7, I'm going to change my color to green. According to Rule 1, 5 and 7, significant. According to this rule, those leading zeros for a small number that just try to kind of tell you magnitude, okay, are not significant.
The first 0 before the decimal would also be incident, or would that be significant?
No, you're right. I'll go ahead and clear that up.
I was making
No,
sure.
but a lot of times students don't necessarily put it.
Yeah.
So then let's go back to what Aaron said. Let's write a different number. 1.0, bless you, 0.0057. Okay, Rule 1 says this number is significant because it's not 0. 5 and 7 are significant. Okay, and according to rule number 2, okay, so in case your eyes are going buggy, what we got 4, we got 7 here. So 7 significant figures. That's a lot. And then how many do we have over here? 2. Yep, 2 significant figures. Okay? Any questions? And then last but not least, we're going to talk about how do we clear up this ambiguity. I love the word ambiguity, okay? But if you're ambiguous, you're like, yeah, wishy-washy, okay? So this one, again, is about zeros, but it's trailing zeros, and actually this is for a large number. Next to this, if you want to. I don't know, it helps me. Okay, this is talking about a large number. I'll give you an example of this. So what if we had 1,350,000? 1,350,000. Where is the decimal? Yes, right there. I agree. And actually, I did this the other day. I'm going to go ahead and pick on green. I'm going to put the decimal there. I agree. And I'm going to put dots around it. And I don't know if you remember, but I call that an implied decimal. when somebody implies something, it's like, you know it's there. Okay, it's an implied decimal. Okay, so this says they're ambiguous. Let me finish this thought and I'll kind of revisit it here in a minute. The convention is if somebody didn't take the anchor the time to go ahead and put that decimal, they're like, dude, those zeros don't count. Basically, the uncertainty starts here in the the 20,000s place, okay? So, put another way, according to Rule 1, we take the first 3 digits, okay? According to what we're going to talk about a little bit more is if you don't know where the uncertainty begins, we're not going to count those zeros. I'm going to put X's over them. I'm going to show a way to clean up this ambiguity. But overall, I'm going to say question mark. We'll revisit this momentarily. Are there any questions about the other rules, though? Okay, so now you can see on the next page, go ahead and take a stab at those. Let's go ahead and next to each one, say how many significant figures there are. And here in a minute, I'm going to have you hold up fingers. This works pretty good because I don't think we have any more than 5. Okay.
Also, when I got set 18 fours wrong.
Okay. So how many significant figures for the first one? Awesome. It is 4. Let me know if you have any questions. How many significant figures for the next one? 5-ish. I'm liking it. Very good. Significant figures here. 3. Perfect. Sig figs. Back to 5 again. Okay, sig figs. Any questions? 2? There are 2. Why are there 2? What rule are we applying?
The leading zeros do not count.
Yep, the leading zeros do not count. Very good. Perfect. Okay. Okay, let me see. How close are we to an assignment slide? Okay, so I've got some slides that kind of talk about the significance of significant figures. But instead of going to that, I want you to jump to this slide so we can get to the assignment slide. And I'll go back and revisit those tomorrow. Okay, can everybody find this slide? Okay, good. So this is that last rule, right? The large number, and you have those trailing zeros, right? So the thing is, the way this works is, according to Rule 1, significant. If that last digit, and I know I'm kind of mixing thoughts here, but I'm going to go ahead and put a question mark over the 2 in the 1000s place. It's significant, 2 significant figures. But if that's the case, can you see where our uncertainty is plus or minus, 1,000? Does that make sense?
A little bit.
Okay. Let's say they had a fancier, something fancier than all that, and let's just say that actually the uncertainty started over there in the hundreds place. It just happened to be, maybe they had a digital scale that read the 0 number, but they knew to the nearest hundreds. Okay, I'm going to have to erase this if I can. And then down here with regard to uncertainty, that'd be plus or minus 100. that make sense? Well, let's say that it just so happened that the measuring device they were using actually could say to the nearest tens.
So plus or
Okay.
minus 10 then.
Mm-hmm. That gives me 4 sig figs, and that is plus or minus 10.
So then,
It just rounded off that way.
okay, and I guess I'm kind of jumping ahead here, but for the fifth number, if it's significant, then it would be plus or minus 1,
Mm-hmm.
because we're just following the place value of the numbers.
Mm-hmm. You know, and
Okay, I get it now.
and that when they talk about it being ambiguous, I mean that's what they mean. They're like, I don't know what you are talking about. It's not clear to me. Okay, so this is where I said it's becoming somewhat of an accepted convention that if the decimal is shown, okay, and actually I'm going to say when we show the decimal, that is what we call an explicit, not implied. But when it is shown, you're going to hear me use the word explicit. Okay? Not implied, not like mysterious. Somebody used the ink to put that decimal there. Okay? If that's the case, and they cared enough to do that, then like in the case before, all 5, you know, the uncertainty started out there in the ones place. Okay? So in this case, if we revisit that large number with those trailing zeros, but instead of implying the decimal, we explicitly put it there, 5 sig figs. Okay. One other thing about, I guess this would just apply to large numbers. Another way is to pack it up with scientific notation. That's coming up in a minute. Okay, so still with the ambiguity. If they explicitly put the decimal, then clear out to the ones place. That's where the uncertainty begins, with those zeros. If they don't put the decimal, then you got to be conservative. If they didn't put the decimal, then if we revisit the 32,000 with just an implied decimal, you got to go with 2 sig figs. That's what this is saying. That's it. Okay, that rule number 5. So it kind of boils down to, and again, there's one more way around it with scientific packing up a number that's large in scientific notation. But if you don't, you got to be conservative if it's implied, and if it's explicitly put there, go with significant. Okay. So scientific notation can be your friend to kind of clear things up. So here's the deal, and actually I was looking at my notes this morning, I'm like, I don't think I ever said this. But what's that first part, starts with the letter C? What's the first part in something in scientific notation?
Coefficient.
Coefficient, yep. So you have your coefficient, I'll just put an example, 7.930 times 10, I'm just making up an example, times 10 raised to the 15th power. Okay? Yep, so this is the coefficient. And the cool thing about this is basically those 5 rules that I said before, you apply those 5 rules, you evaluate this. Ooh, fancy word. Evaluate for SF, significant figures. Okay, so you evaluate the coefficient for significant figures. So how many significant, okay, get your fingers ready. Get your fingers ready. Look at the coefficient. How many significant figures? Yay! I'm liking it. Okay. Okay.
She's
Very
just
good.
gonna always be like this to you now.
Okay. So let's revisit that 32,000. Packing up that 32,000, it looks like this. Of course, you move the decimal place over until you get a number between 1 and 10, 3.2, and that's times 10 raised to the 4th. So how many sig figs there? 2. Very good. Oh, it already says. 3 sig figs here. 4, 5. Okay, does that make sense?
Yes.
So you use that scientific notation to your advantage.
Makes things easier.
It does. It
Count out all those.
clears up the ambiguity. I know. So let's take a look. These will be due Wednesday. These will get you, like I said, I'm going to come back and revisit those other slides, but that should be fine. So you have 44. Okay. Remember that they kind of come in pairs, so if you're a little squeamish about 44, you can look at 43 and the answer's in the back of your book. Not too bad.
That's what I did with the homework from last time too.
Yeah.
That really helped out.
And notice that what your author, and I admire him for doing this, is going to force you to rewrite the number. I just think that's a good idea because it talks about, it wants you to clearly draw on there. So we're all on the same page. Let's see, the next one. Let's see, this glare. There it is, okay. So also 46. How many sig figs are there? Now you wouldn't have to rewrite it, but you could. Number 48 wants you to correct their mistakes. And I think that's that it. You aren't. It's not assigned. Somebody show me your side.
Oh, I'm Yep.
Okay. Don't do 5-0 for now. We're going to do it Wednesday. We're going to talk about rounding Wednesday. So for now, just do the.
44, 46, and 48.
Yes, thank you. 44, 46, 48. Okay? All right. See you Wednesday.
I have to run all the way down to the other, and just do